Welcome to the video lesson for section 2.5, the fundamental theorem of algebra. We're going to be looking at several different functions and trying to find all the real and complex zeros of our functions and looking at some behaviors of different polynomials. Let's get started. Let's begin by looking at how many roots or zeros a function could have. And that's going to be directly related to the degree of the function. For our first function, we have f of x is equal to x, and that's going to have a degree of 1, and it turns out that's how many roots it's going to have. For our second function, we have f of x is equal to x squared, and that's going to have either 2 or 0 real zeros. And the reason why it has 2 or 0 is because we have to account for the possibility of complex roots, and those complex roots always show up in pairs. So for this example, if I had 2 real zeros, then I would have no complex zeros. If instead I had 0 real zeros, then I would have 2 complex zeros. We're going to use that idea when we look at the rest of our functions here. For our third function, x cubed, we're going to have either 3 real zeros or 1 real zero. Again, the reason why the change is if we had 1 real zero, that means that the other 2 would actually be complex. As we keep the pattern going, for our next example, x to the fourth, we could have 4 real zeros, we could have 2 real zeros, or we could have 0 real zeros. For x to the fifth, we could have 5, 3, or 1 real zero. And then for the last one, x to the sixth, we could have 6, 4, 2, or 0 real zeros. Again, the amount of real zeros and complex zeros always have to add up to be the actual degree of the function. So if I had 3 real zeros for x to the fifth, that would mean the other 2 zeros would have to be complex. If I had 2 real zeros for x to the sixth, that means that the other 4 would have to be complex zeros. And again, just remember, complex zeros are always going to come in conjugate pairs. This leads us into the fundamental theorem of algebra, and that states that if f of x is a polynomial of degree n, where n is greater than 0, then our function f has at least one 0 in the complex number system. Let's read that again. Again, if our polynomial of degree n, where n is greater than 0, f has at least one 0 in the complex number system. We'll see how that factors in with the rest of our examples as we move along and we find the real and the complex zeros for our polynomials. All right, looking at our linear factorization theorem, it states that if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors. And when we're talking about writing something as a product of linear factors, we're saying exactly that. You want to write down each factor of the function. So we have the first factor, the second factor, all the way to our last factor. And we've also discussed the fact that these could actually be complex values, where C1, C2, and Cn are in fact complex numbers. So as we are working on factoring out our polynomials, we're going to have the real factors, and then we're also going to have the complex factors because we are completely factoring our polynomials based off of this linear factorization theorem. All right, for our first example here, we're going to try and find all of the real and complex zeros. We could do a lot of things here, but we're going to start off with factoring out the greatest common factor. And if I do that correctly, then I have x and then an x squared plus 4. Now when I want to find the zeros, I'm going to set these equal to 0. And I can actually go ahead and solve each one of these expressions. So for the first one, our first factor, we just set x equal to 0, and we're all done. For our second factor, x squared plus 4, I can set that equal to 0. And now that we've discussed the idea of complex values, we can finish solving this expression and get the complex zeros. All right, so we're going to go ahead and subtract 4 on both sides, which gives me x squared equal to negative 4. Then I'm going to go ahead and take the square root on both sides. And one thing that we have to consider here, and something I got to consider for most of the chapter, anytime we're taking the square root of a value, do we need to add in plus or minus? And for this chapter, the answer is usually going to be yes. And in general, the answer is going to be yes. So I'm going to go ahead and simplify my left side. And when I simplify the right side, I get plus or minus the square root of negative 4, which is going to be plus or minus 2i. So now I have been able to capture all of my zeros. I have my real 0 of x equals 0, and then I have my complex or imaginary zeros where x equals plus or minus 2i. And if I look at the original function, the degree was x cubed, and I have 3 zeros. I have 1, and then this plus or minus gives me the other 2 for a total of 3 zeros. So we can very quickly check to make sure that our work at least checks out with our polynomial. All right, for our following question, we have x cubed minus 3x squared plus 4x minus 2. We want to go ahead and try and find all of the zeros of this function. Now, we're not giving anything to start with. If I look at my last example, I could try the technique of doing some factoring, but I am not the best at factoring a cubic, and this one is a little bit more challenging than I'd like it to be. So one aid that we can actually use for these type of problems is we can go ahead and graph the function. And by graphing the function, we should be able to find all of the real zeros, and then use that to our aid in trying to find all of the complex zeros. All right, so here we have the graph of the function, and as you can see, we have 1, 0. It crosses over the x-axis at 1, and so that means that x equaling 1 is a solution, or a 0. We can also just say we have an x-intercept of 1, 0. And what I can do now is I can take that value, and I can use it with synthetic division and my function here to go ahead and try and simplify something, and then use that to find the complex zeros. And one thing to note, looking at the graph, we have exactly one real 0, and I have a cubic function, which means that there are 2 remaining zeros, and those 2 remaining zeros must be complex values, and they also must be conjugates. All right, so I've gone ahead and set up our synthetic division here using our a value of 1, and then I've listed the coefficients of each one of our terms. Just to refresh this, we're going to go ahead and take our first term all the way down, and then I multiply that by my outside a value, which is 1. All right, so 1 times 1 is going to be 1, and then I'm going to add down. -3 plus 1 is -2. I take the value I got, I go ahead and multiply it by my outside a value, and I get -2. When I add my 4 and -2 together, I get a +2. And I'm going to multiply it one more time, so 2 times 1 is going to be a +2. And finally, I'm going to go ahead and add -2 and +2 together, and I get 0. And that's exactly what we were hoping for, because that proves or supports our answer that 1 was in fact a 0. What I have now, remember the trick here, we start with an x cubed. Once you do synthetic division, our degree is going to be 1 less, so this is going to be a 1x squared. And then we have -2x, and lastly plus 2. Now I know by looking at the graph that there are no more real zeros. So what I can do now is I can take this function and try and factor it to help me solve for the complex zeros. It's not going to factor very easily, so we have to turn to one of our old tools, the quadratic formula. And just to remind you guys of the quadratic formula, it is -b plus or minus the square root of b squared minus 4ac all over 2a. All right, I'm going to need some more space to finish this, so we're going to go ahead and finish this on the next slide. All right, so we have our polynomial, or a quadratic actually, x squared minus 2x plus 2. We have our quadratic formula, and then we're going to go ahead and identify a, b, and c within our quadratic here. It kind of goes in order, so our first coefficient is going to be a. Our second coefficient is going to be b, and then our third coefficient, or constant actually, is going to be c. Let's go ahead and plug this into the quadratic formula now. Since my b value is a -2, and I start off with a negative b here, I'm going to have the opposite of a -2, which ends up being a +2. And then we have plus or minus the square root of b squared minus 4 times a times c all over 2 times a. I'm going to go ahead and do some simplifying here. So we have 2 plus or minus the square root of 4 minus 8 all over 2, which is 2 plus or minus the square root of -4 over 2. And you can see now that because we have the square root of -4, we're going to have some complex numbers here. I'm going to go ahead and simplify that further, so we end up getting 2 plus or minus 2i over 2. And we talked about this a little bit when simplifying complex values. Notice that all 3 of my terms here are in fact divisible by 2. So I'm going to do that, and when I finish, I get 1 plus or minus I. And that represents my final 2 zeros, 1 plus I and also 1 minus I. Combining that with the value I had for my real zeros, I have all 3 of my zeros for my cubic function. All right, for our next example here, we have x to the 5th plus x cubed plus 2x squared minus 12x plus 8. Once again, this is a rather complicated expression, and we have nothing to start with. We could possibly use the rational root theorem to go through the possible real zeros, and then go through all of those using synthetic division, but that's a lot of work. So what we're going to do instead is, again, graph a function to find the real zeros, and use those to help us simplify down to our complex zeros. All right, so I can see I have some roots here. For my first root, it's going to actually be down here, which is going to be at -2. My second root is going to be at +1. So I'm going to go ahead and write those numbers down so we don't forget. We have one root at -2, one at +1. We also want to note the type of roots that we have. Because this is crossing through, it's an odd root, which means I can do synthetic division with it at least once, but we could do it possibly 3 times. For my second root, because it bounces off, it's an even root. So once again, I can do synthetic division with it twice, possibly more, but we'd have to do it in even amounts, so 2 or 4. But we want to factor that in when we're trying to simplify our expression in terms of how many times we're going to do synthetic division with our root. So just to recap, we have an odd root that crosses through, so I'm going to do synthetic division once with this one. And then I have an even root here, it bounces off, so I'm going to do synthetic division twice, and then we'll see what we're left with and deal with that accordingly. All right, getting started with our odd root, the -2, we're going to go ahead and bring the 1 down and then multiply by our a value. We add those together, multiply again, add down, multiply again, add down, multiply again, add down, multiply last time, and fortunately we did get that 0. Okay, our other value to do synthetic division with was actually our +1. Going to go ahead and move this one down and multiply, and then add. Then we multiply and we add. Multiply and add. Multiply one last time and add. And fortunately, we got another 0. Now that one was actually an even root, so I'm going to do synthetic division with it one more time. We're going to bring this one down and multiply, add, multiply, add, multiply, and add, and we did get another 0. So it's really important to note that our last numbers here were all in fact zeros, supporting the fact that those were roots. And since I saw that I didn't have any other values where my graph crossed the x-axis, I can go ahead and assume I have some complex values here. And even if I didn't, I can solve this because it's a quadratic, and I would finish getting the remaining zeros. Just to verify it is in fact quadratic, I started with something that was to the 5th power. When you do synthetic division, what you result with is 1 less, so this would be to the 4th power, and then to the 3rd power, which means this is definitely going to be squared. So I have 1x squared plus 4. All right, so x squared plus 4, if I want to solve that, I'm going to set that equal to 0. If I subtract 4 on both sides, we get x squared is equal to -4. And if I want to solve this, I take the square root, don't forget doing plus or minus, and we end up getting x equals plus or minus 2i. So I have 2 complex roots, and then I have 3 separate real roots. Together that's a total of 5, and our degree was 5. So we have successfully found all of the zeros for our polynomial. All right, for our next example, we're going to go backwards. We are going to be given our actual roots, so we have -1, 1, and 3i. We're going to use them to help us identify the polynomial. One thing we have to remember, though, is when we're given a complex value, we also have to consider the conjugate of that. So because we're given a positive 3i, we have to factor in that complex roots always appear in conjugates, so we have to add in a -3i. When I take those 4 things, I can write my factors as a linear factor. So we're going to get x plus 1, x minus 1, x minus 3i, and also x plus 3i. I'm going to go ahead and multiply these together. One of the convenient aspects is we do have a shortcut for our conjugates, and these first two are actually the difference of squares. So when I multiply them together, I'm going to actually get x squared minus 1, and then I'm going to get x squared plus 9, using my a squared plus b squared shortcut for my complex values. All right, if I go ahead and multiply that together, then I get as my final answer x to the 4th plus 8x squared minus 9. And now I have my polynomial with real zeros at -1, +1, and complex zeros at 3i and -3i. All right, here's another example where we have real zeros at 2, 2, 1 plus I, and 1 minus I. Now those two things are actually 2 ways we could deal with those first values. Because we see the 2 happens twice, that's our multiplicity, which explicitly gives us our exponent. So we could list that as x minus 2 squared. We could also just say, well, I know I have 2 twice, so I have x minus 2, and then x minus 2. Whichever way makes it easier for you, we're going to multiply it all together in the end, so it's not that big of a deal. When I look at my other 2 values, though, I have x minus 1 minus I, and then we have x minus 1 plus I. All right, the last 2 expressions are going to be a little bit more challenging to multiply together. For the first 2, though, when I multiply x minus 2 and x minus 2, we get x squared minus 4x plus 4. I'm going to go ahead and multiply our second two expressions and put my answer up at the top because I need a little bit of scratch room there because there are a lot of terms to multiply. All right, so I multiply going from left to right, we're going to get x squared minus x plus xi plus, minus x plus 1 minus I minus xi plus I minus I squared. Okay, anything with an I should simplify or cancel out if we've done this correctly. So let's go ahead and look. I have a plus xi and I have a minus xi, so they cancel. I have a minus I and a plus I, so that cancels. And then my minus I squared is going to actually end up being a plus 1. So I can go ahead and write down my simplified expression there. We end up getting x squared minus 2x plus 2. All right, my next task is to go ahead and multiply one quadratic by the next. So we have x squared minus 4x plus 4 times x squared minus 2x plus 2. This takes a little bit of multiplying, so I'm going to go ahead and write down what our final answer is. We get for our final answer x to the fourth minus 6x cubed plus 14x squared minus 16x plus 8. All right, for our final example here, we have a 0, a 0, a 4, and then we have 1 plus 2i. Now, we're only given one of our complex zeros, but we know they have to come in conjugates, which means we also have to include 1 minus 2i. All right, we're going to go ahead and list this out. So I have x squared, and then x minus 4. Then we're going to have x minus 1 minus 2i, and x minus 1 plus 2i. All right, if we go ahead and multiply our first two expressions there, we're going to end up getting x cubed minus 4x squared. And I'm going to go ahead and do what I did with the last example. We're going to multiply these together, and I'm going to list what I get up at the top. All right, so we should get x squared minus x plus 2xi minus x plus 1 minus 2i minus 2xi plus 2i, and then minus 4i squared. Okay, just like with our last example, anything with an I should simplify or cancel if you've done this correctly. So we have a positive 2xi and a negative 2xi. We have a positive 2i and a negative 2i. And then our negative 4i squared is going to end up being a positive 4, which means that for my polynomial, when I simplify it, we should get x squared minus 2x plus 5. All right, our final task is to multiply our two expressions together, x cubed minus 4x squared, and then x squared minus 2x plus 5. We do get something a little complicated when we finally multiply that together. We get x to the fifth minus 6x to the fourth plus 13x cubed minus 20x squared. And that's it. That's it for all of our notes. Go ahead and get started on the homework, and good luck.